And sir, this session will be recorded and it will be uploaded in the IEEE TV and YouTube. With your permission, can we start recording, sir?
Okay, okay.
Dear participants, at the conclusion of the session, a feedback form will be posted in the chat box. Please fill it out before you leave to receive your e-certificates. Shall we start the session, sir?
Okay, can you wait first? Some more participants can join now.
Sure, sir, sure, sir. We'll wait for.
Is it visible screen?
Yes, sir.
Oh, okay, but you can start. Huh?
Okay, sir. Now,
Okay.
let us begin the session with the welcome note.
One book, one pen, one child, and one teacher can change the world. Good evening to one and all present here. Thank you for your presence and for spending your precious time to attend the session of our webinar series, which is awaiting you to give the knowledge which you wouldn't mind taking back to yourself. I welcome you all to the exciting webinar event hosted by IEEE SJCE SB and the IEEE Power and Energy Society SGCE SB INSEGNATE a Spotlight Series.
I'm intrigued by the name Insegnante. What's the story behind choosing this as title?
Great question. The word insegnata is derived from the Italian word for teacher or instructor. As such, it represents as the speakers. The choice of this title reflects our focus on learning from these experienced educators who will impact valuable knowledge and insights in their respective fields, just as a teacher, guide, and enlightenment their students. Our speakers will guide and enlighten our audience through this webinar, making Insegnata a fitting and meaningful title for our series. I am Lal Arjun and my co-host Ziad. It's our privilege to guide you through this captivating journey into the vast expanse of knowledge.
Let's start with speaker's welcome note. Ladies and gentlemen, it is our pleasure to welcome our distinguished speaker for today's session, Dr. P. Anbarasan Sir, Associate Professor, Department of Electrical and Electronics Engineering in St. Joseph's College of Engineering. Today, we are honored to have Dr. Anbarasan Sir to share his insights and expertise on state space modeling of DC to DC converters. His presentation promises to be enlightening, informative, offering us deeper understanding of the subject matter. Dr. Anbarasan serves as an assistant professor in the Department of Electrical and Electronics Engineering in St. Joseph's College of Engineering. With a profound academic background encompassing MTech and PhD degrees, Dr. Anbarasan brings over 14 years of extensive teaching experience to the institution. His area of specialization lies in the electrical drives and control, where he has demonstrated remarkable expertise. Over the years, he has imparted knowledge across various subjects including power electronics, control systems, and digital signal processing. Dr. Anbarasan's contributions extend beyond the classroom with 6 publications in the reputable journals and the organization of 3 workshops. Furthermore, he has actively participated in 9 conferences and attended 15 workshops, enriching his understanding and network with the academic community. Notably, Dr. Anbarasan holds 3 patents showcasing his innovative contributions to the field. His dedication to academic excellence and passion for research make him an invaluable member of the faculty, inspiring students and colleagues alike to strive for excellence. Please join me in extending a warm welcome to Dr. P. Anbarasan Sir. We are grateful for the opportunity to learn from your expertise and looking forward to an engaging and insightful session. Once again, it is our immense pleasure to extend a warm welcome to you. Now the session is entirely yours, sir.
Okay, thank you, Zia. Welcome you all students. Really happy to share my knowledge on DC converter. And it is a combination of what you're going to see is state-based modeling of DC converter. It is a new to you because this is one of the research topic now the most of the faculty are doing on the converter. That is a state-based modeling. Okay, so when you are comes under when you are going for the project and all, initially you will be doing some modeling. Okay, so I'm taking the DC converter. I will have some two or three converter. We have some modeling. Then there will be what is the purpose of modeling. First we will see. Okay, it's a combination of control system as well as power electronics. So even though it is some equation base, it must we need to understand the modeling of converter. Okay. So even though some second year students don't know about the DC converter, you can have some knowledge, some basic idea about the DC converter. Then you can move on to the state-based modeling. Okay. Uh, so initially, what is the DC converter first? Okay. So generally, converters we can say it is a change of one form of power to the another form of power. We can say so. It may be a DC or maybe AC. Okay. But here the DC to DC already I mentioned. So here it will be converting from DC to DC. Then what type of DC we are converting from to another form? So generally it is a fixed DC we can say. So input is the form of fixed DC. It will be converted to the variable DC. So why we are going for variable DC means all the application what you need is a variable DC. You won't need this fixed DC. So this variable DC will be got from the some switching devices. So whenever if you operate with the switching device, if you by operating the switch by on and off, you can get the variable DC. Okay, so fixed DC normally you can get it from the some rectifier and all. So variable DC will be getting from only by switching the switches, either by some MOSFET or IGBT. Okay, so we are DC-DC converter. We can say a chopper also. We can say another name for the particular DC-DC converter. We can say DC chopper. It is nothing but a DC equivalent to AC transformer. So you know heard about the transformer. So transformer normally it will be step up or step down the voltages with the corresponds to the number of turns ratio. The same thing it will be done for the DC chopper. So here the DC equivalent nothing but a only it converts to DC DC, but it may be a step up or it may be a step down the voltage. Okay, so here we have several applications. So since the DC chopper have the several application, even in the renewable integrations, we have the solar, we have the wind. Suppose it is wind and solar, we are going to integrate to the load. We need the DC DC converter. So particularly, what is the purpose of renewable integration means we can reduce the ripple. So there will be some lot of ripple present when we convert the fixed DC to variable DC. So from the solar we are taking the DC. It will be connected to the load means in between will have load side will have some ripples. We have to reduce the ripple. So for that we need the DC converter. Okay. So we can have the different types of converters we'll be using. So nowadays we are having different DC converters. The researchers have found. So initially we have some conventional converters used. Okay. So nowadays different non-isolated DC converter also the researchers have found. So particular main reason we have the reproduction, and also by reproduction what we are getting, we will be getting a can draw the continuous current, continuous as well as smooth input current by using the DC-DC converter. So that is one of the purpose. Another thing we can use it in the e-vehicles. So in the e-vehicles, normally we'll be using DC for the purpose of, so normally will be lighting purpose is there. So for that we need the we can have the converter, step down converter we can have, and also we can wiper is there. So in the car we have the wiper, and also in the window control is there now. So for that window control also we can use the DC-DC converter. So in order to operate that we can have so lighting purpose. Another one more thing, particularly we can use in the e-vehicle, that is the isolation. So the isolation the main purpose, crucial purpose in the case of e-vehicle. So for that we need the, in order to control that we need the DC-DC converter. So not to isolate the input and output side. So normally we have some high voltage side will be there. So for that we need the DC-DC converters. Okay, and also another main application is the regulator. So if you say the DC-DC converter means we can say it is a acts as a regulator. So suppose I want to have some fixed voltage, then we can go for the DC-DC converter by operating in the closed loop condition. So whenever if we operate the DC converter in the closed loop condition, we can have some fixed voltage you can get in the output side. So using that, we can use it in the like a smart lighting also. So smart lighting we can use, and also we can use in the chargers, pumps. So we have the different applications. There are some main applications we are using the DC converters. Okay. So here we can have some conventional topologies. What is the conventional means? Initially, these are three main topologies. Still, we are using this topology. So from the three main topology, we have different topologies have made by the researchers. Still, some of the PhD doing faculty also doing the some DCG converter topologies, new topology they have found, and also they are doing modeling for that. Okay, and they are having some hardware and all they are doing. Okay, so these are the three main topologies, namely buck boost and buck boost converter. So what is a buck means? It will access a step down voltage. Buck means whatever the voltage will be step down it will be given to the load. A boost means the voltage will be boosted up and that will be given to the load side. What is the buck boost mean? The output will have the both the step down as well as step up. You can have the both the buck as well as boost done in the converter. So there is a mainly three element will be using for the all those conventional topologies. One is the switching device. The switching device can have either IGBT or MOSFET, or you can use the SCR depending upon the application or depending upon the switching frequency. Some of the rating of the power we can use the switching device will be varies. Okay, so the switch will be there and we'll have the inductor. So we have to design the inverter. So we'll have the design the corresponding inductor for the converter, and we'll have the diodes will be there. So these are the three main elements. These three main elements will be combination of three elements will be differs for the all those three conventional converters. The switch will be given in the input side here. The boost side will be common to the inductor as well as diode. For the buck boost converter, inductor will be common to the switch and diode. So like that, we'll have the three conventional converter. We'll have the input DC, fixed DC will be there. The output side will be getting the variable DC by controlling this switch. Okay, so whenever the switch is on and off, we can control the output voltage. So the load side will have some capacitor. We'll have the capacitor as well as it will be connected to the load. Okay, so these are the main, these are the conventional circuit. Still we are using in the various applications. So one is a buck boost as well as buck boost converter. We can have the, we are not going to do the operation on this converter. So I'm going to deal with the state-based modeling for this converters. Okay. This is new to the your students. Normally, state-based modeling is will be studying on the control system. Only will be doing on the fifth unit will be in control system. Will be studying on the fifth unit, not the converter modeling, but you will be doing some modeling for the any mechanical device. You can do the modeling. Or basic modeling you can do using state-based analysis. Okay. So before going into analyze the DC converter, we have to know what is the state-based modeling. Why we are going the state-based modeling. So before going to this state-based modeling, you have studied this transfer function. So transfer function is one of the model. So we'll be studying the control system. Normally the transfer function nothing but a Laplace transform output by input with the zero initial condition will be studied. It is one of the type of modeling. Like the same manner of transfer function modeling, the one more powerful tool will be for the modeling of the any system named as a state-based modeling. So we have several advantages over the transfer function modeling. So transfer function modeling is one of the modeling the system in order to analyze the behavior of the corresponding system. So if you want to study the behavior of any system, you will be studying the, you will be doing the modeling of the system. You will be writing the differential equation, and then we have to form the what is the Laplace output by input. One of the another tool will be state-based modeling. So what is the advantage over the transfer function? We have to know. So we have this different system, namely, it may be system may be a linear or it may be a nonlinear. Our system may be a time varying system or time invariant system. Normally it will be named as this system as a LTH system will be same. So system will be named as a LTH system. It is meaning that linear time invariant system. Linear time invariant system. Mostly we'll be using linear time invariant system. So suppose I want to model using transfer function modeling, it will be normally used for the only LTI system, linear time invariant. We can't go for the non-linear system, or we can't go not goes for the time variant system. So that is one of the drawback in the transfer function. So that's why we're going for what is a system named as a state-based modeling. So for state-based modeling, we can go for both linear, non-linear, time varying, time invariant, as well as one more thing. For transfer function, will be giving only one input and will be getting as a single output. So that is a will be named as a R of S as the input and C of S as the output. So R of S and C of S in the Laplace transform. The same, but in the case of state-based modeling, we can't give single input. We can give any number of input. So we can give multiple input or we can get the multiple output. That is one of the advantage in the case of state-based modeling. At a time, we can give multiple input and multiple output. And one more thing, will be having the, we know the definition. Transfer function nothing but Laplace output by input with zero initial condition. But in the case of state-based modeling, we can't go for the zero initial condition. We can neglect the zero initial condition. With the initial condition, we can do the state-based modeling. That is one of the advantage in the case of state-based modeling. And also, it is one of the modern approach for analysis using digital computers. So easily we can incorporate this state-based modeling in the practically in this digital system. So these are some advantage of state-based modeling. Okay. So we have the two modeling. One is the transfer function. Another one is the state-based modeling. So this is one of the best method in order to analyze any system. So here I am going to analyze state-based modeling for the DC to DC converter. Some conversion topology you can get the, I can have the some buck or boost or buck boost. I can have the state-based modeling today. Okay. Okay. So how to state space formation can be done. So what are the things already I told? We have the multiple input will be there, multiple output will be there. Okay. So it won't be very difficult. So if you know this some how to write the Kirchhoff's voltage law, Kirchhoff's current law, if you know means we can easily form the state-based formulation. So what are the things present on the state-based formulation? So normally we have the three vector, normally input vector, output vector, and the state variable vector. So whatever the system, we have to form the three vectors, namely input vector, output vector, and state variable vector. So the input vector will be named as a U, and output will be Y, and they will have the state variable we have to form over any system that will be represented by the X, small x. So this based on this vector, we have to form the state model. So these two equations will be named as a state model. And the state model, we have the two equations named as a state equation and the output equation. So what is the state equation will be normally represented by the derivative of x equal to ax plus bu. So this is the state equation. And we will have the one more equation named as the output equation, y equal to cx plus du. So we have to form these two equations in order to formulate the state space. Okay, so here we have the input vector, output vector. It will be differs for the corresponding system. Suppose based on the state variable. Suppose if we form the state variable, the system has a two state variable means corresponding input vector also two input vectors and output vector will have the two output vector. If we having the three state variable vector means corresponding input vector also varies by 3, and output vector also varies by 3. Okay, so here we have some constant. So we'll have the A, B, C, D, and R. So this will be named as a matrix, nothing but a matrix. Okay, the A will be named as a system matrix, which will have the order of n cross n. So based on the state variable, we'll have the n cross n matrix we have to form. And B is the input matrix, which will be having the order of n cross m. Okay, similarly, we have the C and D. Mostly, these three ABC matrix will be formed for the state-based formulation. Mostly, this transmission matrix will be represented by the T. It will be, we can neglect that. So, transmission matrix will be negligible in the case of state-based formulation. So, we have to know the three vectors, and based on the three vectors, we have to form the state model. So, these two equations we are going to form used for the any buck converter or boost converter or buck boost converter or any DC converter. If you want to form the state-based modeling, we have to know the what is the three vectors and the corresponding equation we have to form. Okay, so we'll have some example. Let it be consider the buck converter. Okay, start with the state model for the buck converter. For that, how to model it? Okay. It won't be very difficult. First of all, we have to know how to model. Modeling is somewhat difficult. There are nothing is that. Okay. So you have to know the operation of any converter first. Suppose any converter is there means earlier I told a converter is a combination of switches, diode, and a inductor. Okay. So this is a buck converter circuit. For that, I am going to model the state-based modeling. So they told we have this state variable will be there, input vector, output vector will be there. Okay, we have to form the two equation, state equation and output equation. These two equation you are going to form the for the buck converter. Okay, so how to form the state equation and output equation for the buck converter? Okay, we can see here. If you have the buck converter, how to if we want to form the state equation or output equation, we have to analyze in the case of two conditions. One is the switch is in the on condition, another one is the switch is in off condition. So whenever switch is on, what will happen? Whenever switch is off, what will happen? This how the switch will be, how the DC converter will be acts. That you are going to see. So let it be considered switch is in on condition. Let it be the S is a switch. Here the L is the inductor, the diode, and C is the capacitor, output side capacitor, and load is there. We can have the any type of load here. So if we consider as the ideal case, you can have the any type of load, and the input voltage I am going to represent by the V. So let it be considered switch is on. So switch is on means it will be closed here. So rewrite the if it is closed. So here this is anode. So this is the cathode. So what will happen? So when the switch is closed means automatically this will be a reverse bias. This will be reverse bias. Automatically the circuit will be closed in the form of inductor. So inductor will be charged and it will be flow through the capacitor as well as load. So if we redraw the on circuit, we can have the circuit like this. So this is the equivalent circuit of whenever the buck converter is on. Is it right? So switch is on. So it will be closed through the inductor. It will be closed and it will be through the capacitor and it will be through the load. It will be current will be flows. Okay. So this is the equivalent circuit for the buck converter. So I am going to form the state model for the that is a state formation equation for on condition first. So we can form for on condition, we can write the state formation as state model, and as well as for off condition also we can write the state model. Okay. So for on condition, how can we write the state model? So whenever any converter, we have to consider what are the charging element present on the converter. What are how many number of charging element present? So we have to check the how many number of charging element. So we have the two charging element present. So one is the inductor, another one is the capacitor. Okay. So we having two charging element, then we can form the two state variables. So number of state variable depends upon this. So this is the state variable. So the number of state variable depends upon the number of charging elements. So we have the two charging element. So two number of charging element corresponds to the two state variables. So else and C, if there is a two inductor will be there means two capacitor will be there means then we can have form the four state variable. So only you have the two charging elements. So it's two state variable, and the state variable can be represented by how? How can we represent? We can represent by the small x. Already I told the x1, x2 are the state variables. Okay. This x1, x2 we are going to represent what? So having the two state variable x1, another one is the x2. Okay. So this x1, x2, you can take the inductor and the capacitor. Whenever the inductor is there means we can consider the inductor current. The inductor we have to consider the current, and capacitor consider the voltage. Okay. So inductor we have to take the current, capacitor means you can take the voltage across the capacitor. So there is a state variable we are going to take. So with the inductor current, so let it be IL is there. IL we can take the variable, and the X2 as the voltage across the capacitor. Voltage across the capacitor I am going to take the VC. So we can take the state variable as a 2. So state variable 2 means automatically, so we can form the state equation x naught equal to ax plus bu. This you are going to write. Okay, A is then A is nothing but n cross n. Okay, then n cross n nothing but this is two variable means the A matrix you can form as a 2 cross 2 matrix. A is 2 cross 2, and the B is nothing but input matrix of n cross m. So based on this vector. So based on this vector, we can form the U matrix. So we can have automatically we can have the U1, U2, two input variables. Okay. So first of all, we can write the equation. So based on the equation, we can form this state space formulation. Okay. So first we have found this state variable, two state variable, nothing but x1, x2. The one is the current through the inductor, another one is the voltage across the capacitor. Okay. So now we can see the state equation, nothing but the x star. X star nothing but derivative of x. Okay. So we have to find the derivative of x1, x2. Nothing but x is nothing but x star is nothing but x1, x1 dot, x2 dot. So this is nothing but x1 dot and then x2 dot. So x1 dot is nothing but derivative of IL upper dIL by dt, and the x2 dot is nothing but derivative of VC. That is voltage across the capacitor is VC. Derivative of VC is nothing but dVC by dt. So that we are going to form that. How to form that? Okay, by writing the equation only. So already we know what is the switching equation. Already we have the on condition. This is the switching circuit. Just apply the KVL as well as KCL. Okay, if you apply the KVL, we can get the one equation. Apply the KCL, we can get the equation. Okay, whenever switch is on condition, just to see here, switch is close to here. Okay, the inductor will be charging condition. The inductor polarity will be plus here, and this polarity is negative here. Okay, and this load side automatically will have the drop, and it will be plus and minus. These two are in parallel. This R and the capacitor will be parallel. So the same polarity will be applied in the VC also. So the V in is a polarity already here having the V in. This is the plus polarity. This is minus. Okay, and the inductor will be charged with the polarity of plus here and a minus here, and we will have the drop on the output side. Okay, just write the KVL equation here. What is the KVL equation? The output voltage, algebraic sum of the voltage in the closed path is 0. Okay, so can here the applied voltage is plus Vn. So we have the current flowing here this side. So the plus Vn, and in the inductor we have the drop. So plus to minus. So we'll have the Vin. So we have the Vin, and we have the minus of VL. Minus of VL. The output side either we can write in terms of output voltage or capacitor, but I need the capacitor. Since we have the state variable, we are taking the IL and the VC. I'm going to write in terms of capacitor. So minus of, since it is in the drop side, we can write as a minus of VC, that is equal to 0. So we have the plus V in minus VL minus VC equal to 0. So we know what is the voltage across the inductor. So nothing but a LDA by dt. So VC I'm keeping as it is. Why means we have the state variable in terms of VC. We have the state variable in terms of IL. Already we have the written the VL as a DIL by dt. Okay, so we got the equation in terms of IL as well as VC, but I need the equation in terms of derivative of IL and derivative of VC. So I need the DIL by dt in terms of one equation and VC by dt in terms of one equation. So from this equation, we can get the DIL by dt as a one derivative. So we can write the DIL by dt as the first equation. So we can write by keeping DL by dt on the other side. We can write V in. So V in you can write and minus VC. Okay, minus VC. So by keeping the L on the other side, so we can Vn by L and the Vc by L. So this is the equation 1 for the DL by dt. So from this we can write the state space formulation. So this is by applying KVL we can got the this equation. Okay. So now we can apply the KCL. The same circuit we can apply the KCL. Okay, for this circuit by apply the KCL in this node. Just apply the KCL in this node. So what are the current here? The algebraic sum of the current meeting at here. This node it will be 0. So let it be considered this node. The current entering here is nothing but IL, and this is nothing but here IC. It will be living here, and this is output current living here. Okay. So this is I naught. So this is IC. Okay. So we can write the equation as IL equal to we can write IC plus we can write I naught. So this is the equation we can get. Okay, but I need the equation in terms of either by d. Already we got dl by dt, one equation. So from this equation, just to get the equation for dvc by dt, I need the equation for dvc by dt. Okay, so IL don't disturb the IL, keep it as it is. IC we can write. How can you write the voltage current through the capacitor? So current through the capacitor nothing but dvc by dt we can write. So IL equal to, so current through the capacitor nothing but C times dvc by dt. So we can write C times dvc by dt as a current through the capacitor, and I naught nothing but what? What is the current through the resistor? So I naught we can write nothing but V naught by R we can write, but this V naught and VC are same. So I equal to V by R we know. The instead of V naught I am putting as a VC. So this VC and V naught are both are same. So we can write instead of V naught put it as a VC. So VC by R. Okay. So we got the equation as IL equal to C dVc by dt plus VC by R. So from this just write in terms of only dVc by dt. So we can write this equation as in terms of dVc by dt equal to dVc by dt equal to, how can you write? So dVc by dt equal to, so IL will have, so we can write IL by C we can write. Okay, IL by C, and we can take that side, we can have the VC by RC. So VC by RC one, right? So this is the second equation. So this is the second equation, and this is the first equation. So we can formulate the state equation as well as output equation now. So we got two equations in terms of dL by dt, dVc by dt. So first, from the first equation, we can have the derivative of IL. From second equation, we can get the derivative of VC. So the VC dot nothing but dVc by dt. Okay. Then we can formulate the what is that? We can formulate the state-based formulation. So now how can you form the state formulation? We can see here. How can you form the state formulation? So x1 dot, x2 dot. So we can form the x1 dot, x2 dot nothing but, so you can see here x1 dot nothing but dL by dt. So this is nothing but x1 dot. X1 dot nothing but dL by dt. Okay. So dL by dt is x1 dot. Okay. So this is x1 dot. And next write the dVc by dt as a x2 dot. So again derivative as a dVc by dt as a x2 dot. Okay. So this is a state equation formation. And next we are going to form the A matrix. So A matrix nothing but 2 cross 2. 2 cross 2 of Nothing but what are the variable? We have the two variable, nothing but IL. Another one is the VC. So this is AX. சரியா? So AX, this is X dot, this is A, this is AX plus BU. BU nothing but 2 cross 1. So this is a B, 2 cross B into U. Here U is nothing but input. We have the input nothing but in VU. So B nothing but 2 cross 1 in terms of B in. Okay. So we'll have the input B in here. Okay. So how can you form this A matrix? How can you form this A matrix first? So you can see the equation. We'll have the variable. So dl by dt is nothing but so here IL coefficient we have to see, VC coefficient we have to see. So first equation, see here, what is the input? There is no IL here. There is no IL here. Okay. Only we have the VC coefficient. Those 0 times IL, what is the meaning that? There is no IL coefficient. That's why I put it as a 0 here. Next, we have the VC is there. VC coefficient nothing but minus 1 by L. So here put the minus 1 by L times of VC. The coefficient of VC, you have to write it here. Okay. Plus, what is the V in coefficient? V in, we have the V in coefficient is present on the first equation. That is 1 by L. So 1 by L times of V in. Okay. Similarly, we can write the second equation. See the second equation. What is the IL coefficient? If there is IL coefficient, then write the coefficient 1 by C times of I 1 by L. So 1 by C times of IL. And second, we'll have the, if there is any VC coefficient. Yes, VC coefficient is the 1 by RC, minus 1 by RC. Put it as a minus 1 by RC times of VC. So this forming the derivative of IL and VC, we can form the state equation. Similarly, we can form the output equation. So this is X dot is the state equation. Another one is output equation, nothing but a Cx plus du. So mostly this d will be neglected since it is negligible one. We can write the C times X, we can write the output equation. We can normally output equation on that we can form. Suppose see the output side. So how to model the output side? See the output side. What are the things present on the output side? From that we can write the equation. Normally this is the output across the load. Nothing but equal to the VC. So we can write the V naught equal to VC. V naught equal to VC we can write as the output equation. From this we can form the output equation. So you can see here output is nothing but V naught equal to, we'll have the 1 cross 2 is the output equation formulation in terms of variable IL and VC. So like this we have to form. So in the output equation, only one variable, only VC is present. There is no IL coefficient. Put it as a 0 for the IL coefficient and put the 1 for the VC coefficient. Coefficient of VC is 1. So 0, 1 times of IL VC is the output equation. So like that we can form the state space model by using state equation as well as output equation. Okay. So this is I am writing only for the on condition. Similarly, suppose if the switch is off. Suppose the switch is off means what will happen? Already the inductor will be charged. Okay. So if the inductor is charged means the switch is open. The switch is open means the input is entirely neglected. So whatever the inductor charge will be again circulated. So whatever the inductor charge will be circulated through the capacitor's load like this. Okay. Whenever the inductor will be discharged, the polarity will be here is a plus and this will be negative. So you have to keep in mind the polarity of the inductor will be plus on this side. Actually, this will be polarity plus and this will be axis negative. Again, we have to write the equation by applying the KVL as well as KCL. So we have to make the again derivative of IL as well as VC. We have to form the two equation and then we have to form the state space formulation. So state space formulation will be done based on the charging element. So based on the L as well as capacitor, we can form the charging element. Okay. So here we can write the KVL equation. Nothing but here the inductor will be this will be polarity positive. Then we can write voltage across the inductor. This will be positive. Already the voltage polarity of load will be this is positive and this is minus. The current flow this direction means VL minus of V naught nothing but VC. Okay, that is equal to 0. So VL minus VC equal to 0 on the equation we can write. Here VL nothing but L dA by dt minus VC equal to 0. Okay, and here if you apply the KCL here, the inductor current is IL Okay, so IL is the incoming current, and IC is the outgoing current, and then one more outgoing current, nothing but the load current. We can say I naught. Okay, so IL equal to IC plus I naught. So IL is nothing but, we can keep it as it is, IL. The current of the capacitor we know. So C times of dVc by dt. C times dVc by dt is the IC current, plus I naught is nothing but current through the resistor, nothing but V by R. Okay, so instead of V naught by R, we can write Vc by R. Instead of V naught, put it as in terms of Vc, since it is the state variable. Okay, already we have formed the IL, and we both are in terms of Vc. Okay, so from this equation we can form, from the dVc by dt we can write as the dVc by dt equal to, you can write in terms of dVc by dt, in terms into C you can write IL by C, then we can write minus of Vc by Rc. So this is the second equation for the off condition. Okay, for first equation normally you can form from this we can write dL by dt. So dL by dt nothing but, so first equation form dL by dt. So dL by dt equal to, so we can write Vc, so Vc into, sorry, Vc by L. So this is the first equation. So we can write the dL by dt coefficient and the dVc by dc, what are the coefficient present. So you can see the first equation. So there is no IL term, put it as a 0, and we'll have the Vc, the 1 by L is the coefficient, and the second we can have the dVc, but check the dVc by dt. So IL coefficient is 1 by C. Okay, IL coefficient 1 by C, and minus 1 by RC is the coefficient of Vc, and there is no input term. There is no Vn term for the both the equation. Put it as a 0, 0. So there is no input term for the both the equation. Put it as 0. And in the case of output voltage, V naught equal to Vc. Here also V naught equal to Vc. Okay. So coefficient of Vc is 1. So I am putting as a 0 and a 1. So we can form the two output equation. So sorry, two state model for both the on condition as well as off condition. So these are a state model. So from this state model, sir, what are the things we can do? So we have formed the state model. Then what are the things we can do? Using the state model means, suppose I want to analyze a system. So I want to analyze the converter system for any application. Suppose I want, what are the things we can analyze means, we can analyze the behavior of the system. Suppose whether the system is stable or not. Yes, we can analyze. Compared to transfer function modeling, if you form the state-based modeling, you can analyze the stability, you can analyze the system behavior. So suppose I want to create a system. Suppose I want to create a system. Before that, we can model the equation, and then we can check it up using the equation in the system. You can easily check it using the MATLAB itself. Okay, if you write the system equation means, you can check using the modeling equation. You can check in the MATLAB. I can check in within the 5 minutes. You can check the system stability, system behavior, all those things you can check using the state model. Okay, so this is the advantage compared to the transfer function. So transfer function also we can write the equation, but we can have some disadvantage. You can't do the initial condition and all. For suppose the initial charging condition and all will be considered as 0 in the case of transfer function. But in the case of state-based modeling, the initial voltage in the capacitor, initial current, if you consider for the inductor and all, will be considering for the state-based model. Okay, this is the advantage. The same manner, so this is analyzed for the buck converter. Okay, the same manner we can analyze for the boost converter also. Whenever if you model the state model, we'll be analyzing both on condition as well as off condition. So we have tried the applying the KVL. What are the charging element we have to see? Okay, so how many number of charging, based on the charging element we have to form the number of variables, state variables. Okay, so for the boost converter also we have the one single inductor as well as single capacitor. Okay, so we have to take the state variable as the current through the inductor and voltage across the capacitor as a state variable. The current to the inductor will be derivative you have to take, and the voltage across the capacitor, derivative of voltage of capacitor we have to form. Okay, Then you have to form the both the on condition, write the KVL equation as well as KCL equation, then form the state model. And the state model will consist of both state equation as well as output equation. Okay, and the operating condition are very simple. Very simple. And when the switch is on means just to close the switch and see the condition. Whenever switch is closed means the current flow will be flow only through the switch only. It won't go to the diode. So it won't go through the diode. It will be entirely cut off. Okay, then the switch is non condition. The switch is closed like this. Already if there is a capacitive charge condition, then the voltage across the capacitor will be charged through the capacitor resistor like this. Okay, so this is the equivalent circuit for during non condition. Then we can apply the KVL and write the equation. By apply the KVL, we can write the one equation in the this closed path. That is the V in is the input voltage. And the voltage capacitor is the VL. Already I told whenever the charging condition, it will be charged the polarity of plus here and the minus here. Then we can write V in and polarity is plus here minus means the KVL we can write V in minus VL equal to 0. Okay, so voltage across the inductor is L dA by dt. So V in minus L dA by dt equal to 0. We can write, we can from this we can form the dL by dt. Okay, similarly we can apply the KCL in the node here. Since we need the dVc by dt. So based on this we have to find the write the equation. So by applying the KCL here, so here the current flow is, will be same. The IC, the current to the capacitor will be just opposite polarity of current to the resistor. So we can write the IC plus I naught equal to 0. We can write. Okay. So from this I naught nothing but VC by R and the current to the capacitor is C dVc by dt. From that we can find the dVc by dt. So from this we can find the state model as well as output equation. The same thing we can analyze for the off condition. So whenever the switch is in off condition, you can see here, you can see the this circuit. So whenever switch is in off condition, so okay, this will be open and redraw the circuit. So current flow through the inductor like this. Okay, and we can form the current flow through the diode will be there. So equivalent circuit will be formed like this. Okay, inductor, diode, and capacitor. Okay. So we can see we can write the V in KVL, apply the KVL. So we have the voltage across the inductor, voltage capacitor. Okay, so V in. So whenever it is in off condition, switch is in off condition, the inductor polarity will be here, and the discharging condition this will be the plus. Okay, so plus VL, V in plus VL minus of VC. So polarity this will be same always, plus minus of VC equal to 0. So already V in is there, keep it as it is. VL we can write the voltage across inductor L dA by dt. Okay, minus of VC equal to 0. Okay, so using the equation, you can form the state model for the off condition. Okay, so this can be extended to buck boost. So I am not given the state model for the buck boost. This say almost similar will be coming for the buck boost. So you can model the buck boost. Okay. So with this I stop here. So some of them ask some questions and all. I'll be answering this. Okay. Okay. So see the questions. What are the things? So how good learning state-based modeling benefit the field of okay. So how would learn state-based modeling benefit the field of renewable energy, sir? So normally renewable energy will be applying the DC-DC converter actually. Okay. So DC-DC converter will be applied in the renewable energy. That is the application. Suppose I want to analyze the whole system. Suppose I want to analyze the stability of the whole system. Then we can go for the state-based modeling. State-based modeling, one of the writing some suppose we are going to analyze the behavior of a whole corresponding system means you can go for the state-based model. Okay, suppose renewable system instead of input voltage will be having the solar. Understand? So instead of input voltage, we'll have the solar. Okay, it will be connected to the load. So in between we'll have the converter. Okay, so we can, by modeling the state-based modeling, we can analyze the behavior of the system. Suppose I want to know the stability means, we can analyze. Suppose I want to analyze the behavior of the corresponding system for the different input. Okay, then you can go for the analysis. That is the state transforming benefit in the renewable energy. Okay, what is the scope of development in the state-based model? Scope is nothing but, again, the same answer. The state-based model is nothing but a we can compute easily when compared to the another modeling. Suppose I want to compute in the efficient manner easily, means you can go for the state model compared to the transfer function. And also, suppose I can have some several input system is there, means you can go for the state model. But in the case of transfer function and all, it will be only you can have the single input, single output. But the case of state-based modeling, you can have the multiple input, multiple output. That is the advantage. Okay. Why is the state-based modeling in DC converter being studied? That is the same answer. First of all, modeling is nothing but writing some differential equation. That is a modeling, you can say. Okay, here the state-based modeling nothing but will be writing the equation based on the state variable. We have to form the state variable based on the number of charging element. Okay, what are the various analysis measures used in state-based modeling, and how it is used to improve the efficiency of system? Various analysis measures is that. So this is one of the modeling. Okay, analysis measures means we can have the transfer function analysis, one of the method. State-based modeling is one of the method. But here also we can consider the different condition is there. In advantage and advanced manner and all, I'm not I didn't say that. Suppose here also we can have some continuous current is there, continuous current will be there, discontinuous current will be there. Okay, for that and all we can analyze the different measures. So I'm not considered for that. We can have the modeling. We have that two types of modeling. We can form the control system. Okay. And sir, can you please explain the role of DC converter in transformers, and how does state-based modeling help in processing it? So transformer it will be different part. So I told DC converter is nothing but a similar to a transformer. See, nothing but a DC transformer. The transformer is nothing but step down, step up voltage. Okay. Role of DC converter in transformer, it will be definitely differs. Okay. So it's similar to a DC transformer. We are having this step up or step down the voltage in the AC side. Similar to that, we can have the DC converter. We can step up or step down the voltage. Okay. So you can do the modeling, state modeling. We can do it for the any converter. Take any converter, just do the modeling equation, and then you can work out for the equation. You can further you can do the stability. And final year project and all, you can do it the any system. Normally, any students, you can take any converter and do the modeling equation. Okay, then apply the stability using the MATLAB. By using the state equation, we can analyze the stability. So using that, basically two equations. Basically, using the two equations on and off condition, we can analyze the stability for any converter. Okay. Instead of input voltage, we can connect the renewable system. We can analyze in the hardware also. So simulation also we can check. So we can analyze any behavior. What are the behavior if you want to analyze? We can analyze the time response behavior. Yes, we can analyze. If you want to analyze the frequency response behavior, yes, we can analyze. Okay. So there are some advantages, and we can efficiently analyze the using state-based model compared to the other types. That is the transfer function model. Okay. So this is starting state-based modeling are new to you. Okay. But if you understand state-based modeling, it will be very interesting. Normally, you will be studying this some basics of state-based representation in the 15th unit in the control system. This is somewhat advantages for any converter. If we apply, and we can see what are the things we can analyze. Okay. So, is there any other question also you can ask? Okay.
Thank you for the wonderful session presentations and answering the questions, sir. It was a really an informative session for us. Now, now I'd like to call to distribute a gesture of appreciation to our resource person for the day. Dr. Anbarasan P. Sir, kindly accept the e-memento as our token of gratitude, sir.
Thank you, Pa. Thank you. Actually, this is somewhat difficult for understanding in 1 hour. If there are any doubt or if you want to analyze in the state models, you can approach. Okay. So it will be some basic. You can get it from the control system of Unit 5. And if you want to analyze in the final year, suppose you want to do some project, so you want to write the equation, and it will be surely how to publish paper means you have to write the equation. Okay. So for that, it will be useful for you. Okay. So if you go for the higher studies also, it will be helpful to understand the state-based modeling. And also, if you go for the industry and all, if suppose you want to understand the behavior also, you can do the state-based modeling. Okay. Thank you. Thank you for asking questions and passionately listening. Thank you. Thank you very much.
And sir, with your permission, can we have a group picture? I request all the participants to turn on the camera. Thank you, sir, for capturing the memento as we bring the session to a close. Let's proceed with the vote of thanks.
On behalf of the entire INSEGNANTE team and our student members, I want to express our heartfelt appreciation for your enlightening presentation on state space modeling of DC to DC converters. Your insights onto leveraging IEEE resources to empower student members in their career pursuits very truly invaluable. Your expertise and passion undoubtedly inspired us and provided a clear roadmap for navigating the path to success within the IEEE community and on. Thank you, sir, for your dedication to nurturing the next generation of leaders, for sharing your knowledge with us today. Your presentation has a lasting impact, and we look forward to applying knowledge and insights gained to drive positive change in our own endeavors.
Thank you, Pa. Thank you.
We would like to express our heartfelt thanks to all the volunteers who dedicated their time and effort to make our event a resourcing success. Their hard work and commitment have been invaluable. We are pleased to introduce our dedicated volunteer, poster done by Ziad, e-memento done by Ovia, hosting content done by Hariprasad, feedback link created by Sanjana. Hosting was done by Ziad and Lal Arjun. Each of them has played a crucial role in ensuring that our event runs smoothly and leaves a lasting impact. We also want to thank our HOD, our SB advisor, Dr. Jayarama Pradeep ma'am, and SB counselor, Mr. Srikant sir, for their support. Thank you once again to our wonderful team of volunteers.
Okay. Thank you, Pa. Thank you, all the IEEE team. Thank you.
Thank
Thank
you,
you,
sir.
sir.